The universe was once smaller than an atom, and then it blew up. In a fraction of a second, so tiny it defies comprehension. All of space itself expanded faster than the speed of light. This is the cosmic inflation era, the wildest, most pivotal moment in the story of everything, and we are about to explore 25 of its deepest, most mind-bending mysteries. By the end, you will have a front-row seat to the very edge of known physics, where our understanding of reality itself is put to the test. We will ask what could have triggered such an impossible event, and whether this single burst created not just our universe, but an infinite number of others. What is the one cosmic mystery you find most compelling? The first and greatest mystery is what could have possibly begun it all. What flipped the cosmic switch, setting off that unimaginable expansion? To even attempt an answer, we have to introduce a ghost, a phantom field that physicists believe once permeated the infant universe. They call it the inflaton field. Picture it not as a thing you can touch, but as a kind of cosmic landscape, a field of potential energy that filled all of space. In this model, the universe began trapped in a peculiar state known as a false vacuum. This is a deceptive kind of stability, like a ball resting precariously on the very peak of a hill. It seems balanced, but it is filled with an immense pent-up energy, and it is desperate to roll down. All it needs is the tiniest of nudges. That nudge, cosmologists propose, was a random quantum fluctuation. In the seething chaos of that primordial moment, a tiny bubble of the inflaton field spontaneously dropped to a lower, more stable energy level. This event, happening in a volume smaller than a subatomic particle, released the colossal latent energy of the false vacuum. That energy did not create matter or light yet. Instead, it poured directly into the fabric of space itself, causing it to stretch at a ferocious, exponential rate. Inflation was born. The runaway expansion was that ball finally rolling down the hill, converting potential energy into the very engine of creation. Yet here is the profound puzzle, the ultimate first cause question. We have no direct evidence for the inflaton field. We do not know what laws governed it or why the universe was in that false vacuum state to begin with. The trigger remains a ghost in the cosmic machine, a theoretical necessity that explains so much of what we see, while itself remaining just beyond our grasp. But if inflation was a runaway expansion, a cosmic engine stuck in overdrive, then a second, equally vital mystery emerges. How did it ever stop? This is known to cosmologists as the graceful exit problem. For our universe to exist as we know it, that ferocious stretching could not last forever. It needed to shut down, and it needed to do so with incredible precision. Think of the inflaton field as a spring wound impossibly tight during the false vacuum state. Inflation was that spring violently uncoiling. For the graceful exit to occur, the spring had to reach the bottom of its unwind, settle into its lowest energy state, and then somehow transform all that pent-up motion into something new. In the cosmic model, this moment is called reheating. It is the pivotal instant when the energy of the inflaton field finally decayed, dissipating into the primordial universe. This decay did not happen quietly. It was a violent, chaotic transformation where the pure energy that had been stretching space converted itself into a seething, ultra-hot soup of fundamental particles, quarks, electrons, photons. This was the true beginning of the hot Big Bang, the fiery genesis of the matter-filled cosmos. The challenge for physicists is crafting a model where this transition happens smoothly and completely across the entire inflated region. If the decay was patchy or uneven, we would see catastrophic imperfections in our universe today, vast empty voids or bizarrely dense regions that simply do not exist. The fact that our cosmos is so remarkably uniform on large scales tells us the exit was indeed graceful. But the mechanism behind it, the specific rules that guided the inflaton field's decay, remains one of the great unsolved puzzles. We are left wondering what cosmic law acted as the off switch, bringing a violent end to the most violent expansion so that everything else could begin. The very fabric of space-time should still be ringing from that explosive birth. This leads us to the third great mystery, the hunt for the most elusive echo of inflation, primordial gravitational waves. If the inflationary era was as violent as we suspect, it would not have just stretched space, it would have shaken it. The sudden, colossal release of energy should have sent powerful tremors through the very foundation of reality, creating ripples in space-time itself known as gravitational waves. These are not like sound waves or light waves. They are literal distortions in the geometry of the universe, stretches and squeezes in the distance between points. Inflation would have generated these ripples on a universal scale, embedding a faint, fossilized pattern into the oldest light we can see, the cosmic microwave background. That afterglow of the Big Bang, which blankets the entire sky, is our most ancient photograph. Theorists realized that the ferocious gravitational waves of inflation would have left a specific, twisted imprint on the polarization of this light, a distinctive curling pattern known as B-mode polarization. Finding this pattern in the CMB would be the smoking gun, the direct, undeniable proof that inflation truly happened. The search for this signal has become one of the most dramatic quests in modern cosmology. Experiments like BICEP, located at the South Pole to take advantage of the cold, dry, stable air, stare relentlessly at the cosmic microwave background, their instruments fine-tuned to detect the faintest whisper of that primordial curl. The drama peaked with the BICEP-2 announcement in 2014. The team reported they had detected this exact B-mode signal, a discovery heralded as potentially Nobel-worthy. The scientific world held its breath. Had we finally heard the echo of creation? Further analysis, in collaboration with data from the European Space Agency's Planck satellite, revealed a heartbreaking complication. The signal BICEP-2 detected could largely be explained by interstellar dust within our own galaxy, dust that can mimic the very polarization pattern they were seeking. It was not a definitive detection, but a powerful lesson in cosmic humility. The hunt, however, is far from over. Newer, more sensitive experiments continue to scan the heavens, each one peeling back another layer of foreground interference, getting closer to the primordial signal. Why is this search so crucial? Because these gravitational waves come directly from the energy scale of inflation itself. Detecting them would tell us not just that inflation occurred, but how powerful it was, offering a direct line back to the physics of the universe's first fraction of a second. It is the difference between inferring a storm happened from the debris it left behind and actually hearing its thunder. We are still listening for that thunder, and what we might learn could rewrite our understanding of reality's first moment. That near miss in the hunt for gravitational waves underscores just how precise our cosmic evidence must be, and it leads us directly to one of the most compelling reasons scientists believed in inflation in the first place. This is the fourth mystery, known as the horizon problem, and it is a paradox so fundamental it threatened to unravel our entire understanding of the early universe. The evidence comes from that same ancient light, the cosmic microwave background. When we map its temperature across the entire sky, we find something astonishingly uniform. No matter which direction you look, the temperature of this primordial glow is the same to an incredible precision, varying by less than 1 part in 100,000. This seems reasonable until you consider the speed of light. In the standard Big Bang model without inflation, there simply was not enough time since the beginning of the universe for light or heat or any influence to travel between one distant region of the sky and another. Think of two friends standing at opposite ends of a vast, dark field, each holding a candle. If they are too far apart, the light from one candle cannot reach the other to share its warmth. In the early cosmos, the regions that emitted the light we now see in opposite parts of the sky were like those friends, separated by a distance so vast that not even a signal traveling at light speed could have connected them before the light was emitted. They were beyond each other's cosmic horizon, forever out of causal contact. They should have had no way to coordinate their temperature, and yet they are identical. This is the horizon problem. How could the universe be so perfectly mixed if its parts never had a chance to communicate? Inflation provides an elegant and breathtaking solution. It proposes that these vastly separated regions were not always strangers. In the unimaginably dense seed of the pre-inflationary universe, all of space that we now see was compressed into a volume smaller than a proton. Every part of our observable cosmos was crammed together in intimate contact, able to easily exchange energy and reach a uniform temperature. Then inflation struck. That tiny, uniform patch was stretched by a factor of at least 10 to the power of 26. Regions that were once neighboring particles were suddenly hurled apart to opposite ends of the observable universe, far faster than light could ever hope to bridge the new gap. The uniformity we see is not a coincidence, it is a fossil, a memory of that original microscopic togetherness. The horizon problem vanishes because the entire visible cosmos was once a single, tiny neighborhood, thoroughly mixed before the great stretching began. It is a solution of profound simplicity and power, turning a glaring paradox into a predicted feature of the cosmic dawn. That perfect uniformity is only half of the cosmic miracle written into the ancient light. The other half is a hidden geometry, a secret about the very shape of the universe that inflation also had to solve. This is the fifth mystery, known as the flatness problem, and it asks why the universe is not catastrophically curved. To understand this, you have to think of the cosmos as a whole having a shape, a geometry dictated by the tug-of-war between two fundamental forces. On one side, you have the kinetic energy of expansion, the outward thrust from the Big Bang trying to pull everything apart. On the other, you have gravity, the collective pull of all matter and energy trying to collapse the universe back in on itself. The balance between these two forces determines cosmic geometry. If the density of the universe is too high, gravity wins. Space curves in on itself like the surface of a sphere, eventually leading to a big crunch. If the density is too low, expansion wins, and space curves outward like a saddle, leading to eternal, lonely dissipation. But if the density is just right, a perfect, critical balance, then space is flat like an infinite sheet. This flat geometry allows for a stable, long-lived universe where structures like galaxies can form. The problem is that this balance is unimaginably precarious. For our universe to appear as flat as it does today, some 13.8 billion years after the Big Bang, its initial density at the very beginning had to be fine-tuned to an astonishing precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To put that in perspective, it is like balancing a pencil on its tip for billions of years, a feat of such ludicrous perfection it screams of coincidence. This is the flatness problem. Why does the universe seem so exquisitely balanced on this razor's edge? Once again, inflation provides a powerful and elegant answer. It acts like a cosmic magnifying glass of unimaginable power. Imagine you have a tiny, wrinkled piece of foil, crinkled with all sorts of curves and bends. Now imagine stretching that foil until it is the size of a continent. From your local perspective, standing on its now vast surface, all those original wrinkles and curves would be stretched so smooth they would become imperceptible. The surface would appear perfectly flat to you. Inflation did exactly this to the fabric of space. No matter what the initial curvature of the infant universe was, whether it was slightly closed like a sphere or slightly open like a saddle, the exponential stretching of inflation enlarged it by such a colossal factor that any curvature was smoothed out across our entire observable horizon. What we perceive as a perfectly flat universe is not proof of an impossible initial fine-tuning, but rather the inevitable result of that phenomenal stretching. Our local cosmic neighborhood is just a tiny, flat patch on a potentially vast and still curved whole, much like how the Earth feels flat beneath our feet even though it is a sphere. Inflation takes a profound mystery of fine-tuning and transforms it into a natural prediction, turning a cosmic coincidence into an unavoidable outcome of that first violent growth spurt. But if inflation smoothed our universe into a flat, uniform expanse, it forces us to confront an even deeper and perhaps unanswerable question: what existed before the inflationary era began? To even ask this is to venture to the very edge of meaningful physics, into a realm where our concepts of time and causality may simply break down. Our best description of gravity, Einstein's theory of general relativity, works flawlessly when woven together with our understanding of the very small quantum mechanics. Yet at the extreme energies and densities that existed at the moment of inflation's start, these two foundational pillars of physics clash violently. The point where our equations dissolve into nonsense is called the Planck time, an interval so brief it is to a second what a second is to the age of the universe. Before this boundary, our notions of a smooth, continuous spacetime are believed to shatter. We cannot reliably apply the idea of a before in a realm where time as we know it may not have existed at all. It is like asking what is north of the North Pole. The question itself might be flawed, yet the human and scientific impulse to look beyond the horizon is irresistible, leading to highly speculative but fascinating models. One prominent idea is eternal inflation. In this picture, the inflaton field never completely settles down everywhere. Instead, our entire observable cosmos is just one bubble that formed and stopped inflating within a much vaster, eternally inflating multiverse. In this endless sea of hyper-expanding space, new bubble universes are constantly nucleating like bubbles in a boiling pot, each with its own random properties and perhaps even its own laws of physics. Our entire cosmic history, from inflation to galaxies to us, is just a local event within an infinite, timeless foam of creation. Another compelling thought is a cyclic universe. Perhaps our Big Bang was not an absolute beginning but a transition. In some models, the universe undergoes endless cycles of expansion and contraction, a cosmic heartbeat across eons. Each big crunch does not end in a singularity, but instead reaches a maximum density before bouncing back into a new period of expansion, driven by a new phase of inflation. Our universe is then just the latest iteration in an infinite sequence, with each cycle erasing the details of the one before it. A related concept is the quantum bounce, where the collapsing universe of a previous cycle is saved from total destruction by quantum effects, a repulsive force that overcomes gravity at the smallest scales and triggers the bounce into a new expansion. These ideas are not just science fiction, they are serious, albeit untested, extensions of our physical theories. They represent our minds straining to see past the ultimate veil. The profound mystery of what, if anything, came before inflation may be fundamentally unanswerable with any data we can ever obtain from within our cosmic bubble. It pushes our understanding to its absolute limits, reminding us that some horizons might remain forever beyond our reach, not for lack of curiosity, but because the very nature of reality changes at the beginning. This relentless stretching of space holds a staggering implication, one that pushes the very definition of reality to its breaking point. The seventh mystery is the multiverse hypothesis, the idea that our entire cosmos is just one island in an infinite archipelago of universes. This is not mere speculation, but a direct, some would say unavoidable, consequence of the theory of eternal inflation. Remember that ghostly inflaton field, the engine of the expansion. In the eternal inflation picture, this field never completely settles down everywhere. Instead, think of it as a vast, rolling cosmic landscape of energy. Most of this landscape is at a high energy level, causing space to inflate at a ferocious, exponential rate forever. but here and there, random quantum fluctuations cause a tiny patch of that field to drop into a lower energy valley, like a bubble spontaneously forming in a pot of boiling water. When this happens, inflation stops inside that bubble. The energy of the field is released, reheating that local region into a hot, dense soup of particles, and a new, distinct universe is born with its own Big Bang. Crucially, the inflating space outside the bubble continues to expand at an unimaginable rate. This means new bubbles are constantly forming in the gaps, forever out of reach of one another, each one a separate, self-contained cosmic realm. The process is eternal and infinite, generating a multiverse, a sea of bubble universes where our entire observable cosmos is just a single, insignificant speck. The truly mind-bending part is what happens inside each of these bubbles. The specific way the inflaton field settles down, the precise details of its decay, could determine the very laws of physics within that newborn universe. The strength of gravity, the mass of an electron, the number of spatial dimensions that stabilize, all of these fundamental constants could be randomly frozen into different values in different bubbles. In some universes, gravity might be so strong that stars form and burn out in an instant. In others, the forces might be too weak for atoms to ever bind together, leaving a cold, dark, empty expanse. Our universe, with its perfect balance allowing for atoms, stars, planets, and life, would then be no more than a lucky roll of the cosmic dice. We do not live in a specially tuned cosmos. We simply live in one of the rare bubbles where the numbers came out right for complexity to emerge. This idea finds a strange partner in string theory, a leading candidate for a theory of everything. String theory suggests there are not just 3 dimensions of space, but many more, perhaps 10 or 11, most of which are curled up into sizes smaller than an atom. The way these extra dimensions curl and twist determines the laws of physics in our observable 3-dimensional realm. String theory allows for a colossal number of possible configurations, a landscape of perhaps 10 to the power of 500 different solutions, each representing a different possible universe with different physical laws. This string theory landscape aligns eerily well with the bubble universes of eternal inflation. Each bubble could represent a different point in this landscape, a different random stabilization of those extra dimensions, yielding a different set of physical constants. This brings us to the fierce debate at the heart of this mystery. Is the multiverse a profound, testable prediction of our best cosmological theories, or has it crossed the line into untestable metaphysics? Proponents argue it solves the fine-tuning problem elegantly. There is no mystery why our constants seem perfect for life, because in an infinite multiverse, every possible combination of constants exists somewhere. We, by necessity, find ourselves in a universe that can support us. Critics counter that this makes the theory scientifically hollow. If every possible outcome exists in some other universe, then our theories can predict everything and therefore explain nothing specific about our own world. More damningly, if these other universes are forever causally disconnected from us, hidden behind horizons of inflating space that no signal can ever cross, can we ever gather evidence for their existence? Some scientists search for potential scars on our cosmic microwave background, a faint imprint from a collision with another bubble universe in the distant past. Others look for subtle statistical anomalies in the distribution of galaxies, but so far no such evidence has been found. The multiverse remains a breathtaking possibility, a logical extension of our most successful cosmic story, yet it teeters on the edge of science, challenging us to define where the line is between a prediction of physics and a philosophical statement about reality itself. The multiverse idea suggests our laws of physics are just a local accident, but the universe we actually see tells a different, more intricate story. It is a story of delicate imperfections, and that brings us to the 8th mystery, the origin of all cosmic structure. How did a universe smoothed flat by inflation ever produce the magnificent tapestry of galaxies, clusters, and vast cosmic voids? The answer lies not in perfection, but in the microscopic imperfections of the quantum world stretched to cosmic proportions. During the inflationary era, the inflaton field was not a placid, uniform sea. It was a quantum entity subject to the fundamental uncertainty that rules the subatomic realm. At these unimaginably small scales, empty space is not truly empty. It is a frothing, bubbling cauldron of virtual particles popping in and out of existence. This quantum jitter meant the energy density of the inflaton field had tiny, random fluctuations. In one minuscule region, the field might have been ever so slightly more energetic, in another, ever so slightly less. In the ordinary world, these quantum ripples are immeasurably small and fleeting, but inflation acted like the ultimate cosmic amplifier. As space expanded exponentially, it stretched these infinitesimal quantum ripples in the inflaton field along with it. Regions with a tiny bit more energy inflated slightly slower, while regions with a tiny bit less energy inflated slightly faster. By the time inflation ended, these minute differences in the expansion rate had been blown up to macroscopic scales, imprinting minuscule variations in the density of the universe. The smooth cosmic sheet now had a faint, random pattern of hills and valleys in its density, a blueprint written in quantum noise and enlarged across the entire sky. These are the primordial density fluctuations, the seeds of all future structure. After reheating, when the universe was filled with a hot, dense plasma, these density variations meant some regions had just a little more matter and energy than others. Gravity, always an opportunist, began to work on these seeds. Over hundreds of millions of years, the slightly denser regions pulled in more material from their surroundings, growing steadily heavier and more pronounced. The valleys became vast cosmic voids, while the hills collapsed under their own gravity, first into dark matter halos, then pulling in normal gas to form the first stars and galaxies. Every galaxy cluster, every spiral arm, every planet, and every one of us originated from those amplified quantum whispers. This is not just a beautiful story, it is a prediction with stunning observational confirmation. Those primordial density variations left their signature on the cosmic microwave background. As the hot plasma cooled and released the first light, the slightly denser regions appeared as very slightly cooler spots in the CMB, and the slightly less dense regions as slightly warmer spots. This creates a specific speckled pattern across the entire sky. The detailed statistical properties of this speckled pattern, how common hot and cold spots of different sizes are, were precisely predicted by inflationary theory. When satellites like COBE, WMAP, and finally Planck mapped the cosmic microwave background in exquisite detail, they found a near-perfect match to the inflationary prediction. The pattern of fluctuations is exactly what you would expect if they were born from quantum jitter stretched across the cosmos. It is one of the most successful predictions in the history of cosmology, turning an abstract idea about the first fraction of a second into a direct explanation for the large-scale structure of our universe today. We are, in the most literal sense, the children of quantum uncertainty, our existence written into the fabric of reality by the random tremors of an inflating field. The quantum seeds that grew our galaxies solved one cosmic riddle, but they were not the only ghosts inflation had to banish from the early universe. There is another, more tangible phantom particle that should be everywhere, yet we have never found a single one. This is the ninth mystery, known as the monopole problem, and its solution is one of inflation's most elegant triumphs. To understand it, we have to venture into the realm of grand unified theories. These are ambitious ideas in particle physics that suggest the three fundamental forces we know today, the strong nuclear force, the weak nuclear force, and electromagnetism, were not always separate. In the extreme heat and density of the universe's first moments, these forces were merged into one single super force. As the cosmos expanded and cooled, this unified force underwent a series of phase transitions, like water freezing into ice, splitting into the distinct forces we now observe. Theorists realized these transitions would have created topological defects, stable, massive relics frozen into the fabric of space-time. The most famous of these predicted defects is the magnetic monopole. Unlike every magnet we have ever seen, which always has both a north and a south pole, a magnetic monopole is a hypothetical particle that carries just a single magnetic charge, either a north or a south by itself. According to grand unified theories, these particles would have been produced in staggering abundance during that first symmetry breaking, as common as protons in the early universe. And here lies the problem, because magnetic monopoles are predicted to be incredibly heavy, perhaps as massive as 10 to the power of 16 protons, and perfectly stable. They would not decay. If they were created in the vast numbers predicted, they should still be here today, saturating the cosmos. Their immense mass would have dominated the density of the universe long ago, overwhelming all other matter and causing it to collapse in on itself far faster than it actually did. Our universe, filled with galaxies and light, simply could not exist with such a dense population of these monsters. Yet, despite decades of sensitive searches, from deep underground experiments to scans of moon rock and ancient minerals, not one confirmed magnetic monopole has ever been found. Their absence is a glaring contradiction, a particle physics headache of the highest order. How did the universe get rid of them? Inflation provides a beautifully simple answer. It did not destroy the monopoles, it simply made them vanish by dilution. Think of it like this. Imagine you have a single drop of ink in a small glass of water. The water is deeply, uniformly colored. That is the predicted density of monopoles in the hot, dense, pre-inflationary universe. Now take that glass and pour it into an ocean. The ink is still there, its total number of molecules unchanged, but it is now spread so thin across such an immense volume that finding a single molecule in any bucket of seawater becomes virtually impossible. Inflation was that expansion from a glass to an ocean, but on a scale so vast it defies metaphor. The exponential stretching of space increased the volume of the observable universe by a factor of at least 10 to the power of 78. The number of monopoles created in that initial tiny region remained fixed, but the space between them was stretched to an unimaginable degree. Their density plummeted to effectively zero across our entire visible cosmos. What was once a thick soup became, from our perspective, a perfect vacuum. So, the fact that we do not see magnetic monopoles is no longer a problem for grand unified theories. It is actually a powerful piece of evidence for cosmic inflation. It tells us that a phenomenal, exponential expansion must have occurred to sweep these cosmic relics so far beyond our horizon that they are, for all practical purposes, gone. The silence of our detectors is not a failure, but an echo of that great stretching, a confirmation written in the absence of a particle that should have been everywhere. That solution to the monopole problem, however, opens a Pandora's box of its own. If eternal inflation truly creates an infinite number of bubble universes, then we are forced to confront a mathematical nightmare so profound it threatens to undermine the entire idea of making predictions. This is the 10th mystery, known as the measure problem, and it asks a deceptively simple question. In an infinite multiverse, what does it even mean to be typical? Imagine you're standing in a library that contains an infinite number of books. Somewhere in that endless collection, there is a book that contains the exact story of your life, written in perfect detail. But there are also an infinite number of books filled with nothing but the letter are repeated on every page, and another infinite set where the text is random gibberish. In fact, for any possible arrangement of letters, there are an infinite number of books that contain it. So, if you reach out and grab a volume at random from this infinite library, what are the odds you will get a coherent story? The probability becomes impossible to calculate. Dividing the number of good books by the total number of books gives you infinity divided by infinity, which is mathematically undefined. This is the core of the measure problem for eternal inflation. If the multiverse is truly infinite and eternal, then every possible outcome that can happen does happen, and it happens an infinite number of times. There will be an infinite number of bubble universes exactly like ours, with the same history, the same planets, and even an infinite number of copies of you watching this video. But there will also be an infinite number of universes where the laws of physics are slightly different, and an infinite number where they are wildly different. So how do we determine what is probable? Scientists need probabilities to test theories. Inflationary theory predicts that the quantum fluctuations stretched into cosmic seeds should have a specific statistical pattern, one we see confirmed in the cosmic microwave background. But if we are part of a multiverse, the question becomes, why do we see this particular pattern and not another? The hope was to say, because this pattern is the most common one, the most likely outcome in the ensemble of all possible universes. Yet in an infinite set, most common loses all meaning. Without a way to cut the infinite down to size to define a measure, we cannot say anything is more or less likely. It renders the multiverse idea potentially untestable because it could accommodate any observation we ever make. Some theorists work tirelessly on this, trying to craft mathematical rules to compare infinite sets to find a sensible way to count the uncountable. But so far, no consensus measure has been found that everyone agrees is correct. The measure problem stands as a stark reminder that infinity is not just a big number. It is a conceptual abyss that can swallow our ability to reason and predict. It leaves us wondering if the multiverse, for all its breathtaking grandeur, might be a story that science can never fully tell. The measure problem shows how infinity can break our predictions, but there is another crack in the foundation, one that questions whether we can trust the story of inflation at all. This is the trans-Planckian problem, and it cuts to the very core of how we understand the universe's first moment. To see why, we need to follow the journey of a single ripple, one of those quantum fluctuations that seeded our galaxies. Inflation stretched these ripples in the fabric of spacetime from a microscopic seed to a cosmic scale. The wavelengths of these fluctuations, which today span millions of light years, were once unimaginably small. So small, in fact, that according to our best models, they originated on scales far, far smaller than the Planck length. This is not just a tiny measurement, it is a fundamental boundary. The Planck length is about 10 to the power of -35 meters, a scale so minute that the classical concepts of smooth space and time are believed to dissolve into a foaming quantum uncertainty. At this domain, gravity itself must be described by quantum mechanics, a theory we do not yet possess. So here is the profound paradox. Inflationary theory uses the well-tested equations of quantum field theory and general relativity to predict the pattern of cosmic structure we observe. But to do so, it must assume that these equations remain valid all the way back to the start of inflation, when the relevant physics was occurring on scales where those very equations are known to be incomplete. It is like using the rules of fluid dynamics to predict the shape of a wave, but then tracing that wave back to a time when the water was not yet liquid, but a cloud of disconnected atoms. The math works beautifully, but the initial assumption is on shaky ground. Does this mean our entire understanding of the cosmic seeds is built on a mistake? Not necessarily, but it is a glaring warning sign. The trans-Planckian problem forces us to ask whether the predictions of inflation are robust or if they are sensitive to the unknown physics of quantum gravity. Perhaps the peculiar quantum nature of spacetime at those minuscule scales modifies the fluctuations in a way that leaves a distinct fingerprint, a signature we could one day detect in the gravitational wave background or in subtle statistical quirks of the galaxy distribution. This is the hope that the universe's largest structures might encode secrets of its smallest possible scales. The problem reminds us that inflation, for all its success, is likely just an effective description, a powerful glimpse of a deeper truth still hidden in the quantum gravitational fog. To truly understand the initial conditions of our universe, we may need to peer past the Planck curtain into a realm where space and time as we know them cease to exist. Our cosmic story has always started with a bang, a moment of infinite density and temperature where the laws of physics break down. But inflation forces us to re-examine that starting pistol. Did inflation truly erase the need for a singularity, or did it merely push that impossible point further back into the unseeable past? This is a profound question about the ultimate beginning. In the classic Big Bang model, if you rewind the expansion of the universe, all matter and energy get squeezed into a single point of zero volume and infinite density, a mathematical singularity where our equations of gravity simply give up. It is the ultimate cosmic dead end. Inflation, however, changes the starting conditions. Instead of a hot, dense soup expanding from a point, the universe begins as a microscopic patch caught in the false vacuum of the inflaton field. This patch is still unimaginably small and dense, but it is not a mathematical point of infinite everything. From this state, inflation takes over and stretches that patch into our observable cosmos. So, in one sense, inflation replaces the fiery singularity of the classic Big Bang with a different, quantum-driven starting point. But the nagging question remains, what was the origin of that tiny patch itself? To answer that, we must venture beyond general relativity into the speculative realm of quantum cosmology. One of the most famous attempts to describe a beginning without a singularity is the no-boundary proposal, put forward by James Hartle and Stephen Hawking. It uses a concept from quantum mechanics where particles do not have single, definite histories, but instead take every possible path simultaneously. The proposal applies this idea to the entire universe. In this model, there is no sharp, singular beginning in time. Instead, if you could rewind the cosmic clock back toward the start, time itself becomes fuzzy and blends into a fourth dimension of space. The universe would have no boundary, no edge in time, much like the Earth has no edge in space. You can travel south forever on the surface of a sphere, but you will never reach a south pole that is an edge. You simply loop around. In the no-boundary proposal, the beginning of the universe is smooth and finite, like the rounded-off tip of a football, not a sharp, singular point. This smooth, finite quantum state could then naturally give rise to a period of inflation. The geometry of this no-boundary universe makes the inflaton field likely to start in that high-energy false vacuum state, triggering the exponential expansion we need. Here, inflation is not the absolute beginning, but the first major event in a cosmos that has a finite but unbounded origin. Another intriguing idea is that of an emergent universe, one that simply always existed in a static, timeless state before quantum fluctuations sparked it into expansion. Or perhaps our universe was born from a quantum fluctuation in a pre-existing eternal spacetime, a bubble nucleating in an infinite void. In all these models, inflation serves a crucial role. It acts as the great amplifier and smoother, taking whatever initial quantum state the universe was in and stretching it into the vast, flat, uniform cosmos we observe. Whether the true beginning was a singularity, a smooth quantum geometry, or an eternal static state, inflation is the mechanism that turns that obscure origin story into the universe we recognize. So, did inflation avoid the singularity? The answer is tantalizingly close to yes. It provides a plausible physical scenario that starts from a state where our known physics can still, in principle, apply, even if that state is wildly extreme. It pushes the moment of ultimate mystery back from a point of infinite breakdown to a moment of quantum genesis. The search for a complete theory of quantum gravity, one that can describe the universe at the Planck scale, is ultimately the search for the true preface to inflation's first chapter. The question of a beginning without a singularity leads us to a more tangible but equally elusive number. We must ask just how powerful was the inflationary engine. This is the mystery of the energy scale of inflation, a single number that holds the key to connecting the cosmos to the quantum world. Think of the inflaton field as a mountain. The energy scale tells us the height of that mountain, the sheer amount of potential energy that was available to drive the expansion of the universe. It is the voltage of the cosmic battery, and we have one direct way to measure it: by listening for the thunder of those primordial gravitational waves. The logic is beautifully direct. The more violent the inflationary expansion, the more powerful the space-time ripples it would have generated. A higher energy mountain creates a more ferocious quake. Those gravitational waves imprint a specific, twisting pattern on the cosmic microwave background, and the strength of that signal is a direct readout of the energy scale. A loud, clear detection would tell us inflation happened at an energy near the grand unification scale, an almost unimaginable 10 to the power of 16 billion electron volts. This is the energy where the fundamental forces of nature are believed to merge into one. It is a realm 1 trillion times more energetic than anything our particle colliders can ever reach. A detection at this scale would be a monumental bridge, using the entire universe as a particle accelerator to probe physics forever beyond our earthly laboratories. It would give us direct evidence for the ideas behind grand unified theories, the very theories that predicted the troublesome magnetic monopoles inflation diluted away. Yet the universe may have taken a quieter path. Inflation could have occurred at a much lower energy scale, producing gravitational waves so faint they might be forever lost in the noise of galactic dust and other cosmic signals. This would still solve the horizon and flatness problems, but it would mean the inflaton field was a gentler slope, and its physics might be closer to energies we can someday probe in other ways. The ongoing, painstaking search for that B-mode polarization curl is at its heart a quest for this one number. Every experiment at the South Pole, every new space telescope proposal is trying to measure the height of that primordial mountain. Pinpointing the energy scale would do more than just complete the story of inflation. It would tell us where to look for the next theory of everything. It would tell particle physicists which lofty energy regimes their equations must describe, and it would tell cosmologists exactly how violent the birth of our observable universe truly was. We are hunting for the signature of the universe's most powerful event, a signature that could either whisper from a lower slope or shout from the summit of unification. The power of inflation's engine is not its only test, for the theory itself stands at a crossroads of scientific philosophy. This brings us to a critical and often uncomfortable question: can cosmic inflation ever truly be proven wrong? For any idea to be considered solid science, it must be falsifiable, meaning there must be some possible observation that could, in principle, prove it false. Inflation makes several powerful, generic predictions that seem to do exactly this. It predicted a universe that is geometrically flat, a claim spectacularly confirmed by measurements of the cosmic microwave background. It predicted that the seeds of galaxies would be nearly scale invariant, meaning fluctuations should look statistically similar on all size scales, another prediction borne out by the detailed speckled pattern of the ancient light. And it predicted a background of primordial gravitational waves, a signal we are still hunting for. If future observations were to show the universe is dramatically curved, or if the fluctuation pattern looked nothing like the scale invariant one, inflation in its basic form would be in serious trouble. A clear, definitive contradiction would force cosmologists back to the drawing board. The problem, critics argue, is the sheer flexibility of the inflationary framework. Think of it not as a single, rigid model, but as a vast landscape of possibilities. Over the decades, theorists have devised hundreds, perhaps thousands, of specific inflationary models, each with slightly different properties for the inflaton field. Some produce stronger gravitational waves, some weaker. Some last a tiny bit longer, others a fraction shorter. This adaptability can start to look like a weakness. If one particular model is ruled out by data, A theorist can often tweak the parameters or propose a new shape for the inflaton potential to fit the new observations. This raises a profound concern. If you can always adjust the theory to match any new fact, does it actually explain anything at all? Does it become a theory that can accommodate everything and therefore predict nothing specific? This is the delicate line between a robust, flexible scientific theory and one that is so adaptable it becomes untestable. The true test for inflation's scientific integrity lies in its core generic predictions. If we were to discover, for instance, that the universe possesses a preferred direction or a giant, impossible structure that inflation's smoothing effect could not possibly allow, that would challenge its very foundation. The ongoing quest is to find those sharp, unavoidable predictions that all or most inflationary models must obey, and then search the sky for violations. It is a process of boxing the theory in, constraining its endless possibilities until only the most truthful ones remain. The story of inflation is not yet sealed, for its greatest strength, its elegant explanatory power, is perpetually balanced against the risk of its own beautiful flexibility. But a theory's flexibility can sometimes feel like a retreat, a way to avoid being proven wrong. This is precisely why the 15th mystery is so vital, the existence of alternatives to inflation itself. For any scientific idea to remain strong, it must face genuine competition. What if the cosmic horizon and flatness problems have a completely different solution? Several bold theories propose exactly that, challenging the inflationary narrative at its core. One compelling alternative is the bouncing universe model. In this picture, there was no absolute beginning from a singularity. Instead, our expanding cosmos is the rebound phase of a previous contraction. A prior universe collapsed in a big crunch, but instead of ending in a point of infinite density, quantum gravity effects created a repulsive force that caused it to bounce back outward. How does this solve the horizon and flatness problems? During the long, slow contraction before the bounce, the universe has essentially infinite time to homogenize and smooth itself out. Any irregularities or curvature are ironed away by this prolonged period of collapse, much like how crumpled paper smooths when pressed flat. The bounce then transfers this smooth, flat geometry to the new expanding phase we inhabit. Another radical idea comes from the quest for quantum gravity, called emergent gravity. In some approaches, like loop quantum cosmology, the very fabric of spacetime is woven from discrete quantum threads. Near the Planck density, these threads create a repulsive force that naturally prevents a singularity and triggers a rapid but not exponential expansion. This brief quantum bounce can similarly smooth and flatten the universe without requiring a separate inflaton field. Then there is string gas cosmology, born from string theory. It proposes that before the Big Bang, the universe was a hot, dense gas of the fundamental strings from which all particles are made. This gas was trapped in a small, winding space where strings could not easily move. As the universe expanded, these strings unwound, releasing energy and driving a period of slower, power law expansion that could still homogenize the cosmos. Each of these ideas offers a different pathway to the smooth, flat universe we see, without invoking a dedicated period of exponential inflation. So why does inflation remain the dominant story? The answer lies in its detailed, quantitative success. Inflation not only solves the classic problems, it made a specific, risky prediction about the pattern of cosmic seeds, the nearly scale invariant spectrum of fluctuations imprinted on the cosmic microwave background. When satellites like Planck measured that pattern, it matched the inflationary prediction with stunning precision. Most alternatives struggle to naturally produce this exact, observed signature without fine-tuning their own parameters. Furthermore, inflation's framework connects elegantly to particle physics ideas like grand unification, yet the value of these alternatives is immense. They force proponents of inflation to sharpen their arguments, to identify the unique, testable predictions that only inflation can make. They explore the consequences of different quantum gravity theories, reminding us that our current physics is incomplete. These competing ideas are not just backup plans, they are the essential pressure that keeps the entire field honest, driving innovation and preventing any single story from becoming dogma. The true history of the universe's first moment is still being written, and the final chapter will belong to whichever theory can withstand the relentless test of evidence. The smooth geometry inflation left behind was supposed to be a blank, empty stage. Yet the universe we observe today is not just expanding, it is accelerating apart. This acceleration is driven by a mysterious force we call dark energy, and its simplest explanation resurrects a ghost from Einstein's equations, the cosmological constant. This is the 16th mystery, and it presents us with a numerical nightmare of cosmic proportions, a direct link from the inflationary era to our present cosmic fate. The cosmological constant represents a constant energy density inherent to the vacuum of space itself. Think of empty space not as truly empty, but as a seething quantum foam where virtual particles constantly flicker in and out of existence. According to quantum field theory, this activity should endow every cubic centimeter of vacuum with a certain energy. Now recall the inflaton field, that ghostly landscape whose decay powered inflation and reheated the universe. When it settled into its lowest energy state, its job was supposedly done. But what if it did not settle to zero? What if the true vacuum of our universe still holds a tiny, non-zero energy, a faint afterglow of that primordial field, or perhaps something entirely different? This leftover vacuum energy would act exactly like Einstein's cosmological constant, a gentle pressure embedded in space itself that causes the expansion of the universe to speed up. And indeed, our observations of distant supernova and the cosmic microwave background confirm this acceleration is real. The problem, the colossal problem, is the number. When physicists attempt to calculate the expected value of this vacuum energy from the known laws of quantum mechanics, they get an answer that is wrong by a factor of 1 followed by 120 zeros. This is not a small error, it is the worst prediction in the entire history of science. The calculated energy density is 10 to the power of 120 times larger than the value we actually observe. If the theoretical value were correct, the repulsive force of this vacuum energy would have been so unimaginably strong that it would have ripped apart atoms, stars, and galaxies before they could even form. The universe would be a featureless, accelerating void. The fact that we exist, that structures exist, tells us the actual cosmological constant is almost but not quite zero. This staggering discrepancy is the cosmological constant problem. Why is the vacuum energy so infinitesimally small? Inflation's connection to this is profound. Both inflation and dark energy involve a form of energy inherent to space itself causing accelerated expansion. One was unimaginably powerful and short-lived, the other is incredibly feeble and dominates the universe today. Are they two faces of the same phenomenon, just operating at wildly different scales? Did the inflaton field decay to a value that is not zero, but 10 to the power of 120 times smaller than we expect? We have no mechanism to explain such an absurdly precise cancellation. Some theorists suggest an anthropic answer within the multiverse, that in most bubbles the cosmological constant is huge and deadly, and we simply live in one of the rare bubbles where it is small enough for life. Others search for a dynamic field, like a slowly rolling quintessence, that could mimic a cosmological constant but evolve over time. But the number remains a screaming void in our understanding, reminding us that the greatest energy in the universe's history and the faintest whisper that governs its future are part of the same unsolved equation. The cosmological constant is a ghost from the end of inflation that still haunts us, but what happened to the entity that started it all? The inflaton field powered the most dramatic event in cosmic history, and then, according to the standard story, it simply vanished. Its energy decayed, reheating the universe, and it settled into silence. But is that truly the end of its story, or could this primordial architect still linger in the shadows of the modern cosmos? Its ultimate fate is a mystery that ties directly to the greatest unknowns we face today. One compelling possibility is that the inflaton did not fully disappear. After its dramatic roll down the energy hill, it might have settled not at absolute zero, but into a faint, persistent vibration. This remnant energy, stretched incredibly thin by the expansion it caused, could be contributing to the dark energy that now accelerates the universe. In this view, the inflaton field and dark energy are not separate phenomena, but different phases of the same underlying substance, a cosmic fuel that first exploded in a brief, fiery burst and now simmers as a constant, gentle pressure. Another, even darker idea connects it to the missing mass of the universe. Could the inflaton field have decayed not only into the particles we know, but also into a stable, exotic particle that simply does not interact with light? Some models suggest the lightest particle predicted by supersymmetry, a theoretical partner to all known particles, could be a candidate for cold dark matter. If the inflaton field is embedded within a framework like supergravity, which combines supersymmetry with gravity, its decay products could naturally include these stable, weakly interacting particles. The inflaton would then be the mother of both the visible cosmos and its invisible dark matter skeleton. This idea pushes us into the deepest realms of theoretical physics. In string theory, the inflaton is not a lone field, but one note in a vast symphony of fields, each tied to the way extra dimensions of space are curled and folded. The act of inflation, in this picture, is the process of one of these fields rolling toward stability, while others settle into the configurations that fix the laws of physics and the masses of particles in our universe. The inflaton's destiny is thus woven into the very fabric of reality it helped to create. Its modern-day signature, then, might be hiding in plain sight. If a remnant of the field still subtly fluctuates, it could cause tiny variations in the fundamental constants of nature over cosmic time. A faint shimmer in the laws of physics that ultra-precise atomic clocks or observations of distant quasars might one day detect. Or, if it decayed into a unique form of dark matter, its signature could be imprinted in the way galaxies cluster or in the high-energy particles that occasionally zip through our detectors. The inflaton field may have ended its starring role in the first fraction of a second, but its legacy could be written into every dark matter halo and in the accelerating fate of the entire cosmos, a ghost from the beginning that never truly left the stage. But if the inflaton's legacy is woven into the cosmos, its birth story faces a serious accusation. Critics point to an 18th mystery, a deep irony at the heart of the theory. Inflation was supposed to solve the universe's fine-tuning problems, yet many versions of inflation themselves require an astonishing degree of fine-tuning to work. To produce a universe like ours, the conditions for inflation must be set with almost perfect precision from the very start. Think of launching a rocket to the moon. If your initial trajectory is off by even a fraction of a degree, you will miss your target entirely. Inflation faces a similar challenge. First, the inflaton field must begin in that high-energy false vacuum state. But why would it start there? The theory often simply assumes this initial condition without explaining its origin, effectively pushing the question of fine-tuning back one step in time. Then, the field's potential energy landscape, its shape, must be exquisitely crafted. It needs to be flat enough over a wide enough region to allow for the slow roll that produces sufficient expansion, but it must also have a steep enough drop at the end to trigger a violent and complete reheating. If the slope is too steep, inflation ends almost instantly before it can smooth and flatten the cosmos. If it is too shallow, inflation lasts forever, never giving way to the hot Big Bang. The required flatness of this potential is not a natural feature in many particle physics models. It is a special, delicate arrangement. Furthermore, the initial value of the inflaton field must be set within a very narrow range. Too low and inflation never gets going. Too high and the quantum fluctuations during inflation become so large they rip spacetime apart, creating a chaotic mess of black holes instead of a smooth universe. So, have we really solved anything, or have we just exchanged one set of magical numbers for another? This criticism strikes at the philosophical core of inflation's appeal. Some theorists, however, argue that not all models are created equal. They point to ideas like chaotic inflation proposed by Andre Linde as a more natural, less finely tuned alternative. In chaotic inflation, you do not need a carefully prepared false vacuum or a perfectly flat potential. Instead, imagine the inflaton field as a vast, random landscape with many hills and valleys of different heights. In the primordial chaos, the field would have taken on different values in different places. In most regions, nothing special happens, but in those rare patches where the field accidentally started on top of a very high, broad plateau, conditions would be right for exponential expansion. That tiny patch would then inflate to become an entire universe, while the surrounding chaotic terrain is stretched away beyond sight. In this view, our smooth, flat cosmos is not the product of a perfectly set initial state, but a statistical inevitability in a sufficiently large and varied primordial arena. We just happen to live in one of the lucky, inflated bubbles. This moves the fine-tuning from a requirement of the laws to a selection effect within a larger, more random structure. Yet, even chaotic inflation has its own parameters to adjust, like the overall energy scale. The debate continues, a tug-of-war between elegance and necessity, reminding us that the search for a truly natural beginning, one free of miraculous coincidences, may be the most profound challenge of all. The very fabric of reality might have lost something in that great stretching, a cosmic amnesia written into the laws of physics. This leads us to a profound and subtle mystery, the information paradox of inflation, a question that pits the smooth geometry of our cosmos against the fundamental rules of quantum mechanics. At the heart of quantum theory lies a sacred principle called unitarity. It states that information, the complete quantum description of a system, can never be truly destroyed. It can be scrambled, spread out, hidden beyond recovery, but it must, in principle, be preserved. This principle is famously challenged by black holes, which seem to swallow information forever, creating a paradox that has troubled physicists for decades. Inflation, it turns out, may create a similar paradox on a universal scale. Remember those quantum fluctuations, the seeds of galaxies, born from the jitter of the inflaton field. In the ordinary quantum world, these fluctuations are coherent. They have a specific phase relationship with each other, a kind of quantum memory that encodes information about their origin. But during inflation, something strange happens to fluctuations whose wavelengths grow larger than the cosmic horizon. As space expands exponentially, these modes are stretched far beyond the distance any signal can travel. They are pushed outside our observable universe, effectively frozen. In this process, their delicate quantum phases are thought to become randomized or decohered. The coherent quantum information they carried is lost to us, transformed into a classical, random pattern of density variations. The question is this information truly gone, or is it merely hidden? If inflation is a unitary process, that information must still exist somewhere, perhaps encoded in correlations across the entire universe or in subtle features of the gravitational wave background we cannot yet detect. But if the process is not unitary, if inflation genuinely erases quantum information, then it violates one of the core tenets of modern physics. This would mean the laws of quantum mechanics, as we understand them, break down during the universe's most pivotal moment. It would force a radical revision of our understanding, suggesting that cosmology operates under different rules than the quantum physics of the laboratory. Some theorists argue that the information is not lost but transferred. As modes exit the horizon, their information could be imprinted onto the geometry of spacetime itself, or onto longer wavelength fluctuations, preserved in a form we do not yet know how to read. Others see a more troubling possibility, that the observable universe we inhabit is, in a deep sense, a separate quantum system from what lies beyond our horizon, and the information about its initial quantum state is forever inaccessible, a true loss. This paradox is not just philosophical, it has potential observational stakes. If information is preserved, it might leave faint, non-random statistical signatures in the pattern of the cosmic microwave background, a subtle whisper of quantum memory in the ancient light. Finding such a signature would be a monumental discovery, proving that quantum coherence survived the universe's violent birth. The mystery forces us to ask what kind of universe inflation created, not just in its shape, but in its very quantum soul. Did the Great Expansion preserve the complete history of its beginning, or did it wipe the slate clean, leaving us with only classical echoes of a quantum past we can never fully reconstruct? The quantum information paradox forces us to confront the nature of time itself. Our everyday experience tells us time has a clear direction, an arrow flying from a past we remember toward a future we cannot see. We watch an ice cube melt in a glass, but we never see the puddle spontaneously refreeze into a cube. This one-way street is governed by the second law of thermodynamics, which states that entropy, a measure of disorder or randomness, always increases in a closed system. The mystery is not the law itself, but its starting point. Why was the entropy of the early universe so incredibly, improbably low? This is where cosmic inflation weaves itself into the deepest fabric of our reality, potentially setting the stage for time's arrow. To understand this, picture the universe before inflation as a tiny, unimaginably dense seed. In such a state, matter and energy are in maximum chaos, right? Surprisingly, no. Physicists like Sean Carroll explain that gravity turns this intuition on its head. A universe crammed into a single, hot, dense point is actually a state of very low gravitational entropy. It is smooth, featureless, and homogeneous, like a perfectly shuffled deck of cards where every card is in order. The highest entropy state for gravity is not a hot, dense ball, but a universe scattered with black holes, the most disordered objects possible. So the infant universe began in a state of remarkably low entropy, a highly ordered starting line. Then inflation struck. It took that smooth, low entropy seed and stretched it into a vast, flat, and nearly empty expanse. This process massively increased the volume of the universe, and with that volume, the maximum possible entropy it could contain skyrocketed. Think of it like this. You start with a single, neat box of toys, a low entropy state. Inflation does not scatter the toys. Instead, it builds an enormous, empty warehouse around the box. The toys are still neatly packed, but the capacity for disorder, the sheer number of ways those toys could be strewn across that vast new space, has become astronomically larger. The universe after inflation is left in a state that, while still smooth, is now far, far away from its new maximum entropy. It is a neat box sitting in the middle of an empty aircraft hangar. This created a colossal entropy gap, a steep hill for the cosmos to roll down, and roll down it did. As the inflaton field decayed and reheated the universe, it filled that empty warehouse with a hot, dense, uniform gas, a state of high thermal entropy but still low gravitational entropy. From there, gravity got to work. The tiny quantum density fluctuations, those seeds from inflation, began to clump under gravity's pull. Gas coalesced into stars, stars into galaxies, galaxies into clusters. This is the universe climbing toward higher entropy, not by smoothing out, but by creating intricate structures, because in gravity, structure is disorder. Black holes, the ultimate sinks of entropy, began to form. Each step on this long journey from a smooth beginning to a lumpy, structured, and eventually dark and dispersed future represents an increase in entropy. Inflation, by creating that vast arena and the smooth initial conditions within it, essentially wound up the cosmic clock and let it go. It gave the universe somewhere to go, a direction to move. We remember the past and not the future because we are living in the aftermath of that singular, low-entropy beginning that inflation helped to establish. Our perception of time's flow, the melting ice, the fading memory, all of it may be a direct consequence of that explosive moment of stretching, which left the cosmos with a clear path toward disorder and a reason for time to point the way it does. The low entropy beginning inflation provided seems almost too perfect, for when we look at the map of our ancient universe, we find curious blemishes that do not quite fit the story. These are the observational anomalies in the cosmic microwave background, and they form our 21st mystery. The CMB is the most precise confirmation of inflation's predictions, a nearly uniform tapestry of temperature variations. Yet upon this tapestry, astronomers have found a few strange stitches. The most famous is the so-called cold spot, a region in the southern galactic sky that is significantly colder and larger than standard inflation should allow. It spans a vast area, and its statistical probability of arising from random chance is less than 1 in 200. Is it a colossal cosmic void lying between us and the CMB? A supervoid so immense it cools the ancient light passing through it? Or could it be something far more exotic, like the imprint of a collision with another bubble universe from the eternal multiverse? Then there are the large-scale asymmetries. The pattern of hot and cold spots is not perfectly even across the sky. One hemisphere, roughly aligned with our solar system's motion, shows slightly more power, more pronounced temperature variations than the opposite hemisphere. This is like flipping a coin 1 million times and finding that heads consistently comes up more often when you are facing north. It should not happen in an isotropic universe, one that looks the same in every direction, which inflation predicts. Even stranger is the alignment of the lowest order fluctuations, known as multipoles. When scientists decompose the CMB map into these fundamental patterns, they find that the quadrupole, which represents one kind of large-scale asymmetry, and the octupole, another, appear oddly aligned with each other and with the plane of our solar system. This unexpected coordination has been dramatically nicknamed the axis of evil, because if true, it seems to violate the cosmological principle, the foundational idea that the universe has no special place or direction. So what are we seeing? The most conservative explanation is that these are simply statistical flukes. With the immense amount of data in the CMB map, it is possible, though unlikely, for a few strange patterns to emerge purely by chance. Perhaps our instruments are picking up subtle foreground contamination from our own galaxy that we have not fully accounted for. But if these anomalies are real cosmological signals, the implications are staggering. They could be the first hints of physics beyond the simplest inflation models. Perhaps the inflaton field was not completely uniform, or maybe inflation did not last quite as long as we think, leaving an imprint of a pre-inflationary structure on the largest scales of our cosmos. Some have even speculated they could be a fingerprint of the universe's topology, a sign that space itself is not infinite but wrapped in a complex, finite shape. These cosmic bruises challenge us to look deeper. They are the faint whispers from the edge of our observable horizon, suggesting that the story of our smooth, uniform birth may have a few unexpected wrinkles still waiting to be read. Those strange cosmic bruises suggest the universe may hold deeper secrets, but the very fabric of reality we measure is built on a transformation so profound it challenges our understanding of existence itself. How did the fuzzy, probabilistic world of the quantum give birth to the definite, classical cosmos we see around us? This transition is not just a detail, it is the moment the universe chose its shape. Recall those quantum fluctuations in the inflaton field, the microscopic seeds of all structure. In their origin, they were pure quantum entities. This means they existed in a superposition of possibilities, a blend of many different densities and configurations all at once, much like the famous thought experiment of a cat being both alive and dead until observed. They were not yet the specific hills and valleys that would grow into galaxies. They were a haze of potential hills and valleys. Yet, by the time we see their imprint in the cosmic microwave background, they are fixed classical features. The map of the ancient sky shows a specific, random pattern of hot and cold spots, not a blur of all possible patterns. So what forced the quantum possibilities to collapse into one concrete reality? The answer lies in a process called decoherence. In our everyday world, quantum systems are notoriously fragile. When a particle in a superposition interacts with its environment, say, a single photon bounces off it, that interaction effectively measures the particle. The countless possible outcomes of that interaction entangle with the environment, and the delicate quantum phases that held the superposition together get scrambled and lost. The system is forced to pick a definite state from the menu of possibilities. We say it decoheres, becoming classical. But in the primordial universe, this presents a unique and baffling problem. What served as the environment? In the earliest moments, there was nothing outside the system. The entire universe was the system, a single, self-contained quantum entity. You cannot have an external observer or a larger environment to force decoherence when you are dealing with everything that exists. So how did it happen? Cosmologists believe the answer is that the universe acted as its own environment. As inflation stretched those quantum fluctuations, their wavelengths grew longer than the cosmic horizon, the distance light could have traveled since the beginning. Once a fluctuation mode crossed outside this horizon, it was causally disconnected from the rest of the universe. From the perspective of any observer inside the horizon, that mode became frozen, its quantum information inaccessible. This act of crossing the horizon is thought to have played the role of the environment, tracing over the inaccessible degrees of freedom and causing decoherence. The quantum superposition of possible density variations was lost, and a single, random but definite classical fluctuation was stamped onto that region of space. It is as if the universe, by stretching itself so violently, created isolated pockets that could no longer talk to each other, and in that silence the quantum possibilities had to make a choice. This process imprinted a specific, random pattern across the sky, the blueprint for all future structure. The profound implication is that the classical reality we inhabit, the definite positions of galaxies and the very ground beneath our feet, may have been born from a cosmic act of isolation. The universe did not need an external observer. It became its own witness by the sheer act of its explosive growth, freezing quantum potential into classical fact. That quantum freeze into classical fact gave us a universe, but it left one of its most crucial ingredients hanging in a delicate balance. The Higgs field is the only fundamental scalar field we have ever directly discovered, a cosmic molasses that gives particles their mass. Its discovery was a triumph, confirming a cornerstone of our standard model of particle physics. Yet this very field may hold a secret connection to the universe's first moment, for in the mathematics of fields, the Higgs and the inflaton share a family resemblance. Both are scalar fields, meaning they are characterized by a single value at each point in space, like a temperature reading across a map. This similarity has led theorists to a daring question: could they be one and the same? Could the Higgs boson, the particle we smash in colliders, be the remnant of the field that inflated the cosmos? Models where the Higgs itself acts as the inflaton are elegant and compelling. They suggest a profound unity, that the same mechanism responsible for giving particles their mass also drove the universe's exponential expansion. In these models, at the extreme energies of the early universe, the Higgs field would have taken on a vastly different character. Its potential energy landscape, normally shaped like a gentle valley or a Mexican hat, would have been warped by those high energies into a broad, flat plateau. Sitting on that plateau, the Higgs field could have driven a sustained period of inflation before rolling down into the valley we inhabit today. This would mean the Higgs did not just give mass to the universe's contents, it first created the spacious arena for those contents to exist. The implications, however, venture into unsettling territory. The stability of the Higgs vacuum, the valley our universe currently sits in, is not guaranteed. Our best calculations suggest it may be a false vacuum, not the absolute lowest energy state possible. Think of it as a valley within a much deeper canyon. We are sitting comfortably in the higher valley, but there might be a far deeper chasm below us, a true vacuum with vastly different physical laws. Quantum tunneling could, in principle, trigger a catastrophic event called vacuum decay. A microscopic bubble of this true vacuum could spontaneously form somewhere in space. If this bubble forms, the laws of physics inside it would be different, and the walls of this bubble would expand at nearly the speed of light, converting everything they touch into the new alien reality. This process would be unstoppable and would erase the universe as we know it. The connection to inflation is hauntingly direct. If the Higgs was the inflaton, then our entire cosmos is the product of one field rolling from a high energy state into a meta-stable one. We are living in the aftermath of a cosmic phase transition that may not be the final one. The same quantum processes that seeded our galaxies could, on a timescale of billions of eons, seed our destruction. The terrifying beauty of this idea is that it ties the universe's birth to its potential end through the same fundamental field. It suggests the Higgs is not just a passive ingredient, but an active, dynamic architect whose work may still be unfinished. But the Higgs field's potential instability is a problem born of our incomplete physics. To truly understand the universe's absolute beginning, we must confront the limits of our two most successful theories. This brings us to a frontier mystery, the role of quantum gravity. General relativity masterfully describes the cosmos on large scales, while quantum mechanics rules the realm of the very small. Yet at the moment of inflation start at the Planck scale, these two frameworks clash catastrophically. Our equations dissolve into nonsense. This tells us that inflation, for all its explanatory power, is likely just an effective description, a compelling shadow cast by a deeper, more fundamental process we do not yet grasp. A complete theory of quantum gravity would not just tweak inflation, it could potentially replace it entirely, revealing the true genesis of our cosmos. Two leading candidates, string theory and loop quantum gravity, offer radically different visions of this genesis. In loop quantum gravity, space-time is not a smooth continuum, but woven from discrete, finite loops. This has a stunning consequence for the beginning. As you rewind the cosmic expansion, you do not reach a point of infinite density. Instead, the quantum loops create a growing repulsive force that prevents the singularity. The universe reaches a maximum density and then bounces back outward. This is the quantum bridge, a smooth transition from a previous contracting phase into our expanding one. In this model, the smooth, flat geometry we observe is not created by a separate period of exponential inflation, but is a natural result of the intense quantum smoothing during the bounce itself. The Big Bang is not a beginning but a rebound. String theory paints an even more exotic picture. In some versions, our entire three-dimensional universe is a membrane or brain floating in a higher dimensional space. Imagine our cosmos as a vast, flat sheet adrift in a boundless cosmic ocean. Inflation, in this view, could be triggered by a collision between our brain and another. The immense energy of that collision, dissipated across our entire brain, could have heated it and driven a period of rapid expansion. Alternatively, the inflaton field could be related to the position of our brain within the extra dimensions, its motion through that higher dimensional landscape driving the expansion we see. Here, the quantum gravitational origin is not a bounce, but a collision in a hidden, bulk reality. What both these approaches emphasize is that the incredible events of the first fraction of a second were almost certainly governed by laws where gravity is quantized. The inflaton field, if it exists, would be a quantum gravitational entity. The false vacuum it occupied would be a feature of a quantum gravitational landscape. This deeper perspective reframes our entire search. The primordial gravitational waves we hunt for may carry imprints not just of an inflating field, but of the quantum geometry of spacetime itself. The detailed pattern of the cosmic microwave background might hide statistical fingerprints of a quantum bounce or of extra-dimensional physics. Inflation becomes the phenomenological story, the what happened, while quantum gravity seeks to answer the how and why from first principles. We are piecing together a cosmic origin story with a crucial first page still missing, knowing that the final draft will be written in the language of quantized spacetime. The search for a quantum gravity beginning forces us to confront the ultimate practical test for our ideas. If we cannot travel back to the universe's first moment, could we instead recreate its physics here and now? This final mystery asks if we can ever truly simulate the inflationary era, building a working model of creation itself within the confines of a supercomputer or even a laboratory table. The ambition is staggering and the obstacles are fundamental. To simulate inflation, you must model a quantum field, the inflaton, as it evolves within a spacetime that is itself expanding exponentially. Each part of this description pushes our most powerful classical supercomputers to their breaking point. Simulating a quantum field means tracking not just one value, but a vast superposition of possibilities, an exponentially growing number of configurations that classical bits struggle to represent. Then you must couple this to the dynamic geometry of spacetime, solving Einstein's equations for gravity in lockstep with the quantum field's evolution. The computational cost of modeling such a system, even for a tiny patch of the universe for a sliver of that first fraction of a second, is currently beyond our reach. The numbers simply explode. This is where a new kind of machine offers a glimmer of hope, the quantum computer. Unlike a classical computer that uses bits as zeros or ones, a quantum computer uses qubits, which can be in a superposition of 0 and 1 simultaneously. This allows it to naturally represent the probabilistic, entangled nature of a quantum field. In principle, a sufficiently advanced quantum computer could encode the state of the inflaton field onto its array of qubits and simulate its evolution through the complex equations that describe its roll down the energy hill. It would not simulate a single outcome, but the entire quantum wave function of the early universe, allowing us to see how classical structures like density fluctuations naturally emerge from the quantum haze through decoherence. We could run the simulation over and over, testing different models of the inflaton potential and seeing which ones produce a cosmic microwave background that matches our sky. It would be a virtual universe in a box, a laboratory for Genesis, but we are not there yet. Current quantum computers are noisy and have too few qubits to handle such a complex problem. The journey from today's prototypes to a cosmology machine is a long one, but the path is being mapped. In the meantime, scientists pursue a more immediate, tangible dream, creating an analog of inflation right here on Earth. The idea is to find a physical system in the lab that obeys equations mathematically identical to those of an expanding universe. The leading candidate is a Bose-Einstein condensate, a state of matter where atoms are cooled to near absolute zero and coalesce into a single quantum wave. In this exotic fluid, scientists can create sonic analogs of black holes and expanding spacetimes. By carefully manipulating this condensate, they could simulate an exponentially expanding cosmic background. Ripples in the density of the atomic cloud could stand in for quantum fluctuations in the inflaton field. Researchers could watch as these ripples get stretched and frozen, transitioning from quantum to classical, mimicking the process that seeded our galaxies. While it would not be the real inflation, it would be a powerful analog universe governed by the same mathematical heartbeat. Any discovery in the tank, like a new mechanism for generating fluctuations or a different signature of quantum decoherence, could provide crucial clues about what to look for in the actual cosmos. So, can we ever truly simulate the inflation era? The answer is unfolding on two fronts. In the long term, quantum computers may one day host a full digital twin of our cosmic dawn. In the near term, tabletop experiments with ultra-cold atoms are already beginning to echo the physics of that first moment. We may never witness the true beginning, but we are learning to build its echo, to hold a whisper of creation in our hands and listen for the secrets it still holds. We have traveled from the ghostly trigger of the inflaton field to the infinite shores of the multiverse, from the quantum whispers that built galaxies to the haunting possibility that our laws of physics are but a local accident. These 25 mysteries are not separate puzzles, they are interlocking chapters in a single, breathtaking story. The cosmic inflation era, a span of time so brief it defies human comprehension, was the ultimate act of cosmic craftsmanship. In that fleeting moment, the stage was set, the seeds were sown, and the very arrow of time was notched. It determined the geometry of our reality, filled it with the potential for structure, and perhaps even wrote the first draft of its eventual end. Every galaxy that spirals in the distant dark, every planet that circles a star, and every question we ask about our place in it all, traces its lineage back to that explosive fraction of a second. Our quest to understand this era is more than a scientific pursuit. It is a journey to our own origin point, a struggle to read the faded signature on the birth certificate of existence. Which of these mysteries lingers in your mind? Is it the hunt for the echo of gravitational waves, the chilling idea of the multiverse, or the profound link between quantum uncertainty and the stars above? Share your thoughts below, and if you are captivated by the enigmas of the cosmos, subscribe to join us as we continue to explore the deepest wonders of our universe.